Hello everyone, welcome. Today we are going to discuss about projectile motion simulation. So mainly two things we'll be focusing here. Number one, the height, maximum height up to which the particle rises. Number two, the horizontal range, at what distance it is going to fall on the horizontal surface. These two things we'll be focusing on. For that there are variables. This is one is initial speed. Okay, that is also called speed of projection. It can vary from 0 to 30 meter per second. I'll make it, let's say, 15 meter per second to start with. And then we also have another parameter which is angular projection. It can vary from least 25 degrees to 90 degrees. 90 degrees from horizontal, meaning it is vertically upwards. And then on the right hand side, you can have the object to be projected. You can have your own custom made object, or otherwise you can choose one from here. Cannonball. It looks like pumpkin would be messy. Human being you can project from the cannon, or maybe piano or a car, something like that. You can project different objects. And also you can change the mass of the object being projected. You can also change the size of the object. Bigger ball you can take, or a smaller object. And we can also change the gravity. On the Earth, acceleration due to gravity is approximately 9.81 meter per second square. And if you go to other planets, maybe you can have different. So what is the least they're showing? 5, and the maximum is 20 meter per second square. So we can choose maybe whatever I get. Let's say 9.62 meter per second square. But on the Earth, you should remember it is 9.81 meter per second square. We can also choose air resistance, or you can switch off the air resistance. In reality, you will always have air resistance. It also depends on the altitude. At a higher altitude, density of air would be less. So the effect of air resistance is supposed to be less there. So that is another thing. So for the time being, let's switch off the air resistance. And then I'll start shooting all these objects at different angles. Let's see. I'm taking 15 meter per second and project it. Yes, it went and then it has come back. So now you see it's going to go vertically upwards in a straight line path. It reaches the maximum height. That green dot represents the maximum height. It comes back onto the same point of projection. It falls there. There is no sideway movement here. It's only one-dimensional motion. Now I'll change the angle to different values. Maybe 80 degrees I'll take and project it. Now you see it's going to be a curvilinear path. And then 70. So you'll have an again curvilinear path. Now it's going to be wider path, but the height has decreased. Now you see horizontal range earlier was 8.1 meters. Now the horizontal range has increased to around 15 meters approximately. In the process, the height, maximum height was initially this much. Now it has fallen a little, and then now it has fallen a little more. So as the angle increases, the maximum height is decreasing, but the horizontal range is increasing. 70, and then make it 60, and then project it. So it's going to have lesser maximum height, but the higher horizontal range. It has gone up to 20.3 meters. So make it 50 and then see what would happen. 50. Okay, and then project it. So it's going to have still higher range. Okay. So I think I've taken 49. Let it be, not a problem. I just wanted to see this trend, what happens. How about 40 or 39? Let's take and then project it. Oh, the range has decreased now, you see. Up to there it was increasing, horizontal range, but now the range has decreased. So how about 30 degrees? Okay, projected. Horizontal range is decreasing again, but you see that it is matching with one of the paths. So we'll come back to that, but range has definitely decreased. Height has decreased, maximum height has gone down, and the range has decreased. And if you go for 25 degrees and project it, you will see that the maximum height decreases further, and even the horizontal range decreases. So if you look at the angle of projection, the variation of it, as the angle decreases, maximum height keeps on falling, but the horizontal range increases first up to certain value, and after that it is coming back again. So this is one parameter that we want to understand it. You seem to be having same horizontal range for two different angles. Let's check that. So I'm taking 25 degrees. Probably I'll choose some other object. Let's say car. I'll take a racing car, 2000 kg mass and all that. Let's project it and see what would happen at 25 degrees if we project it. So it is falling there, 17.9 meters. So I want to take the complementary angle to it. Complementary angle meaning if you add those two angles, it should be 90 degrees. So 25 you have. What should add to be 25? What should be added to 25 so that it becomes 90 degrees? So that is 65. 65 plus 25 is 90. So let's make 65 and see what is going to happen. So that's a complementary angle we are looking at, and it goes up certainly height. But if you see that the range is the same, different paths definitely, but the horizontal range is coming out to be the same. So this is one point to be noted. When the angles of projection are complementary to each other, what I mean to say is that if you add those two angles, it should come out to be 90 degrees. You see that the horizontal range is coming out to be equal. That's one important observation. Is it true only for 25 degrees and 65 degrees or any other angle? Let's check. Probably you can make 52 degrees, and then I'll take another object. Probably I'll take a human being, 168 kg human being. That's very huge. Maybe 64 kg. Let's take a realistic value and project the human being from there. Okay, so at 52 degrees you got a bigger range, definitely. All right, 22.6, 22.7 meters. Okay, now let's look at the complementary angle to it. What is complementary to 52? 52 plus 38 would be 90. So 38 is another angle where you expect the range to be same. Let's check it out. Will you have the same range? Yes, you will have the same range, but the paths are different definitely. So this is one important point. Whenever the angles of projection are complementary to each other, the range is coming out to be the same. So that one important aspect. And then let us focus on the object. If you observe here, whether you take a cannonball, project it, same speed and same angle of projection, or you take a pumpkin and project it, same speed and same angle of projection, or you take a piano and then project it, same path. It is, you see that all the objects are indicating same path. The path is identical for the same speed and same angle of projection. You see that the object doesn't matter. You can increase the size, decrease the size, whatever you do. All right, the path would be identical. You take a smaller size piano, you take a very big piano. Also, you can have a very heavy piano, 1000 kg piano you can take and project it, and you see certainly it is going to get smashed, but the path that is taken by the entire that object is going to be the same, identical path. So path of projectile seems to be independent of mass of the object, size of the object, shape of the object. It seems to be the same. So that is one important aspect. But if you add air resistance to it, which is a reality, okay, the moment you add air resistance to it, right, it is not going to go with the same path. You can check it. So you can pause here and guess what would happen. Would it fall short or would it overshoot when you have air resistance? The path that I'm showing already is without air resistance. The moment I add air drag, what would happen? So let's see and what happens. See whether your guessing is correct. You see that the path is deviated, so that the pink one is with air resistance and the blue one is without air resistance. You see that without air resistance it is going further and a little higher, but with air resistance its path got contracted little. And of course it's a curvilinear path, but it won't be a parabolic path, curvilinear path, but range has decreased, maximum height has decreased with the air resistance. So that's another important parameter. And of course we can also vary gravity. I've taken 9.62 meter per second square and we got this. I'll remove air resistance and then make gravity 5 and then project the piano, see where it is going to go. Yes, it's going to be expected to go much higher, and like a Martian, you go to Mars and jump from there, you go, You move like Hulk, jump over the hills for a large distance. But if you go to a planet where the gravity is almost more than double the gravity of Earth, and you project the piano from there, you see that it's going to fall pretty short. Quickly, it is going to come back to the surface. Large range would be decreased, and also the height would be decreased. And that's another important aspect. So maximum range would be the range. Where will I have the maximum range for the given speed? And that is going to happen at 45 degrees. At 45 degrees, you will have the maximum range, because 45 degrees is complementary angle to itself. 45 plus 45 is 90 degrees, na? Complementary angle to itself. So that's where you will have the maximum range for the given g value and also for a given speed of projection and angle of projection. So these are the important parameters that I wanted to discuss. I'll close here. I encourage you to go through this simulation. It's a freely available on the net. Colorado University has offered this free applet. I request you to just have a look at it and play around and see if you can get a feel of it. So this effort is only to get the feel of what is going to happen. Of course, quantitatively you'll have to solve the problem. That's the next step. But qualitatively, so when certain parameter changes, what will happen to maximum height and range and all, just to get the feel of it, this video has been created. Thank you very much for listening to it. We'll get back to you again with another video. Until then, bye. See you.